Okay, Mr. Ilham, you're going to present, right?
Yes.
Okay, so you can proceed. You can share your screen and then start to presenting your work.
Is it my screen clear? Is it my screen clear? Thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. First of all, let me introduce myself. My name is Ilham Akbar Satria. I'm one of the representative of BPTA3, or National Laboratory of Aerodynamic, Aeroelastic, and Aeroacoustic Technology. People well known as LAGG from BPPT. Today, I would like to present our research and our teams, Mr. Matsagusto Andika, me, Ilham Akbar Satria, and Mr. Fadil Hasim, with the title Investigation of Symmetric Crossfly and Angiofly Laminate due to Static Aerodynamic Load on High Aspect Ratio Composite Wing. This is the outline of our research. First, we will talk about the introduction and background, and then we will move on to the wing structure and configuration, and also the aerodynamic loads as well. And then the most part is and then the third part is finite element analysis. And then the last but not least is the result discussion and the conclusion. Okay, let's start from the beginning, the introduction. So as we know that there is many design of aircraft wing. One of the design that become very favorite characteristic is the high aspect ratio wing, because they have lift to drag ratio and many good aspected high aspect ratio wing could be performed well. But besides the high aspect ratio wing have many problems like the specific rank and the stiffness characteristic. And then we will talk about the composite material. As we know that there is many material like alloy, metal, and so on. The composite material is become also the favorite material that used by designer of aircraft, because it can be bioregardant and it's very good friend to the high aspect ratio wing, because the designer could be designed to tailor the material mechanical property according to the designer needs. The composite material consists of the fiber and the matrix. The fiber have a job to the strength and the characteristic, and the matrix have a job to the fiber bond. This is the mechanism of the composite materials. And then the objective of this research, the purpose is to determine the characteristic of the cross-ply and angle-ply laminates on the high aspect ratio wing due to aerodynamic loads with a certain tilt deflection and failure index. This study will perform by finite element methods, and we will use the model using 2D shell elements. And then the second chapter, we will talk about the wing structure configuration, material, and aerodynamic loads. This is the model of our wings, our high aspect ratio wing. It consists the structure of the spar, ribs, and the skin. The wing component can be seen in the table 1. There are main spar, rear spar, skin, and the ribs. And this is the percentage of the weight. And this is the example how the composite configuration apply to the wing skin. We divided into the 5 segments, segment 1 until segment 2, with a certain half span, with a variation of the orientation of the wing of the laminate configuration. And then the material also have the material properties as well, like the alloy material. But the difference between the alloy material, we have the strain allowable. The strain allowable used to perform how the failure characteristic, how the failure criteria perform to this material composite. And then we already talked about the material. We will talk about the load. We generate the aerodynamic load that perform above the wing structure using strength approach. The strength approach has been used many research. It's a method to approximate the load above the wing structure. So we will have the load, wing load above the wing structure like this graph figure 3. As we see that the highest load performed in the root and the tip has the lowest wing load. And then the most sophisticated part is the finite element analysis. The load that we have calculated by using analytic, we will apply to our structure using finite element method. We use the shell element and using quad entry element to make sure the quality of the mesh is good enough. And then after we apply the load, we will apply the boundary condition. This study applied two support. First is fixed that will apply to the spar piece, and the second is the pins that support in the pinhole of the structure using multi-plane constraint. And then to make sure our analysis is good enough and valid enough, we use convergence testing. So for convergence testing is a technique to determine the validity of finite element by run for the several number of elements, and we will make sure that the result is close enough, so we can make sure that our simulation have a validity enough. And then we talk about the composite structure. We can use like for Mises or alloy failure criteria. One of the failure criteria that usually used for the composite is the maximum strength failure criteria. Actually simple. The maximum strength criteria is we will find the failure criteria index that have not exceed the strain allowable that we already mentioned. So our strain of the structure could not be exceed of the allowable strain, and divided between them, we will have a failure index. So it must be not more than 1. And then this is the run log of our result, our analysis. We already run for several run from process 1 until n combination. We vary the combination of the laminate, and then the last part is the result and discussion and the conclusion. So from the several cross and angle ply laminate configuration, the arrangement of the segment have been simulated using finite element method to determine the strength and characteristic. And this is the result of the maximum deflection compared to the half span wing. This is the segment 1, 2, 3, and 5, and 4. And we also run for the combination 1. This is the combination of the cross ply and angle ply. And then this is the failure index. Like I mentioned before, that this value has not to be more than 1 to make sure that our structure is strong enough. So this is the first conclusion that we get. By adjusting the layer thickness in the several rejection, we can be reduced by 10% with the same failure index of the value of 0.61, like shown by the table 9 below. Cross by 1 have the same failure index like a cross by 2, but we can reduce it the weight. And then the second conclusion, that with the same mesh, the angle ply laminate has the better composite structural failure characteristic than the cross ply laminate. However, the maximum deflection is more significant in the angle laminate, cross-ply laminate on the other hand. Has a lower maximum deflection than the angle ply laminate but higher failure criteria. It can be said true because as we know that the cross-ply have the more stiffness, so it can be said that the deflection is more lower than the angle ply element that apply 45 angle. We obtain the excellent strength characteristic by using same structural weight in the cross-ply 5 and angle ply 4 by mixing the cross-ply and angle ply laminate. So before we combine this, the deflection may be decreased 47% and the failure index can be reduced up to 67%. Table 11 is just comparison about the base of different weight. And then last, the conclusion that we have is the composite laminate with the properties of cross-ply and angle ply laminates with a change in the layer arrangement have been studied in the specific part of the skin on the wing, the height aspect ratio. Although both the cross-ply and angle ply laminate have distinct property, the angle ply has a benefit being more resistant of the structural failure in the wing skin than cross-ply. But the cross-ply laminate, on the other hand, they provide more stiffness than the angle ply because the deflection is lower than the angle ply. To make the best arrangement, we must combining the ply and the cross-ply laminate. A better compromise had achieved by combining them, and then we will have to produce the lightweight aircraft wing with a good structural, good stiffness, and also good at the failure index. Also, we have to segmentation the wingspan to reduce our weight of the wing structure. So we will have the lightweight aircraft. And then I think that's all of my presentation. We're looking forward that we can have much discussion on or maybe collaboration between us after this event. You can contact me by using email. I hope that we are always healthy during this pandemic COVID-19 outbreak. Thank you. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Salam. Thank you very much, Mr. Ilham. So maybe I just open one or two questions from the audience. Do you have any questions to ask to Mr. Ilham? Okay, maybe one question from me.
Okay.
The cross ply and the angle ply is applied to the windscreen, am I right?
Yes.
How about the spar, the rib, everything? Is it made from composite as well or from aluminium?
Thank you for the question, Mr. Haris Ahmad. For this research, we only varied the wing skin arrangement. The spar, the ribs also applied using composite actually, but we already have some studied locally that we apply the combining of arrangement of composite for the skin, for the spar, ribs, and also the spar. So in this research, we only focus on the skin because the skin have contribute more weight percentage of our aircraft.
Okay, so how about the material? Is it a UD or woven type material?
This is woven.
Woven. Okay. Okay, thank you very much, Mr. Ilham, for your presentation. I wish you all the best.
Wish you all the best.
Okay, so next presenter, all right, I would like to call upon from paper entitled Performance Analysis of Yellow Cylinder Seed Oil Biodiesel Powered Aeroderivative Gas Turbine Engine by Mr. Linus Bonnet, Mr. Solomon, Kaisan, Ibrahim, and Ismail. So please, any representative from the second paper to present. Okay, for the second paper, I'll call again. The paper entitled Performance Analysis of Yellow Oleander Seed Oil Biodiesel Powered Aeroderivative Gas Turbine Engine. And the authors are Mr. Linus, Mr. Bonnet, Mr. Solomon, Kaisan, Mr. Ibrahim, and as well as Mr. Ismail. So any representative from this second paper to present? Mr. Linus, are you there? I saw the name in the participant list, but no response. Okay, so maybe while for waiting for the second paper to present, so can we move to the third paper in this session? So do we have a representative from the third paper entitled Continuous Wavelet Transform for Vibrational Noise Analysis of Manual Drilling Process? Okay, maybe a representative from Mr. Firdaus Samsudin or Muhammad Hanafi Azami, Firdaus Muhammad Zaki, and Nur Azam Abdullah.
Yes, I'm here, Doctor.
Okay.
Can I share my slide?
Yeah, sure.
Can you see the slide?
Yes, okay.
Okay, thank you. Bismillahirrahmanirrahim, and a very good evening. Thank you, the moderator, Dr. Haris Ahmad. My name is Muhammad Firdaus bin Shamsuddin, and I'm going to be sharing my project entitled Continuous Wavelet Transform for Vibrational Noise Analysis in Manual Drilling Process. For this project, I'm assisted by Dr. Muhammad Hanafi, Dr. Hassan Firdaus, and Dr. Nur Azam from IAEM. Before I move forward, I think it's better for me to clarify that the focus of this project is in the aero manufacturing sector. So let me give some brief introduction into the aero manufacturing sector. First, the aero manufacturing sector right now is spanning global wise. We have a global supply chain, whereas the OEMs, famously the famous OEMs.
Oh, this one.
The famous OEMs are
Okay.
okay. Okay, the famous OEMs are Airbus and Boeing, and then so they hold the design of the aircraft, so they're gonna design the whole aircraft. But instead of doing everything by themselves, so they are separating the aircraft into several sections, and they gave this section into a tier one supplier. For example, okay. This is the OEM. They own the whole aircraft. So they section up the aircraft into maybe fuselage one section, the wing section or one section, the empennage one section, and then they give it to tier one suppliers. So what the tier ones gonna do that they're gonna do the detailed engineering design. They're gonna do the materialization and then probably the testing as well. But the package are very big. So instead of manufacturing the whole station by themselves, the tier one supplier will further separated further broken down the section into smaller packages, and then these will be subcon will be given to a tier two supplier. So tier two supplier, for example here, they broken up the whole empennage into horizontal tail or vertical tail, different section. So they give this work packages to tier two supplier or manufacturer. So tier two manufacturer will manufacture the parts in accordance with tier one's requirements, and then to meet the requirement, the whole requirement set by the OEMs. So why I say that it is a global supply chain, because the OEMs, the tier 1 and tier 2 are located all across the globe. For example, here in Malaysia, we have a couple of tier 2 company. So we supply to tier 1s located in Europe, in North America. So the interaction are spanning global wise. So this is I'm going to go back to this because it is a very important factor in for this project. But before that, let me introduce you on the process of a tier 2 manufacturing. So this is an example of manufacturing flow for advanced composite material in aerospace industry for a tier 2 supplier. So when I say advanced composite material, I'm referring to the carbon or glass fibers pre-impregnated with thermoset resin. So the process start with the raw material incoming. Okay, the raw material will come from the material supplier usually across the globe.
Let me just upload my what did this say?
Can I proceed?
Yeah, please proceed. Sorry for the interruption.
No problem. Okay. Let me start again. The process start with the material incoming, where we have the raw materials coming in bulk, and then we will store it inside our storehouse, the prepared materials in a freezer. We kept it at minus 18 degrees C, and then when we want to use it, we will send it to kitting department. They will cut the material in accordance with the shape of the panels, and then it goes into layout. Okay, here, since it is a pre-prep materials, the layout that we do is hand layout, manual hand layout. So it is a manual process. And then after manual hand layout, everything, we send it to autoclave curing, and then setup for curing. We send to demo to take out the finished panel from the cured panel from the mold tool, and then we send for non-destructive inspection, NDT or NDI, in order to see whether there is some internal defect. This is the main disadvantages of composite, because sometimes there are a lot of internal defect within the material itself that cannot be seen with our naked eye. So we need NDT in order to verify the integrity of the laminate, and then we send it to mechanical process to trim the edge, to drill some holes, to seal the edge, and then after that we send it to paint shop for painting. Maybe some mechanical assembly, just minor assembly, and then it will be inspected. After inspection, everything is okay, and then we will ship it to tier 1 facility across the globe. So this is a concern there, because the customer of tier 2 is tier 1, and it is located across the globe. So the parts that we ship to them must be 100% okay. So if there is any defect, it must be detected within the facility. It cannot escape to the customer. It cannot go to the tier 1 side, because it is across the globe. And this is the issue, because if there is a defective part escape from the plant, from the facility, sent to the customer side across the globe, and it's going to be financial and commercial catastrophe, because they're gonna be a lot of things involved. The quality cost, the cost associated to solve the quality issue is going to be humongous. So taking from this problem, this is and then in conjunction with the right now we have industrial revolution 4.0. So what I'm trying to do is that I'm trying to automate the quality manufacturing system. I'm trying to see whether we can, if we can, to instead of do manual inspection, because the process is manual, most of the process are manuals, and currently the inspection is also manual. So I'm trying to see whether we can change from manual to automation in terms of quality management system. So Okay. This is some example given by Liu and Jiang on smart manufacturing in Industry 4.0. So the aim of this smart manufacturing is to increase the efficiency and increase the quality. So you're gonna have a lot of layers. You're gonna be gonna have sensors installed. You're gonna have some workstation to do calculation, and this is where I'm taking my inspiration to do this project. So, but before we move further, in the industry right now, most of the quality system, there are some quality systems that are automated. However, those automations are largely employs machine vision architecture. They use cameras or videos to physically see the defect, and then the algorithm will analyze the feed, will analyze the video, or will analyze the photo. However, this proved to be I'm going to say it a biggest flaw in aero manufacturing sector, because within aero manufacturing sector, our production rate is very low. I mean, if we compare to for example, in the picture here, F&B industry, they produce it parts per million, maybe in one day. However, for aero manufacturing sector, our production rate is very low. It's only in double digit monthly. So it's very low, and couple it with the diverse geometrical variation from parts as small as our A4 paper to spanning a few meters big. So we cannot have a lot of different setup for different videos and everything. So it's gonna cost us a lot in order to to employ machine vision architecture in aero manufacturing sector. And we are trying to break this mold. So what we are proposing to do, we want to use the vibrational noise of a drilling process. So we focus our project into the drilling hole drilling process. So we're gonna use the vibration of the pneumatic drill gun. We're gonna use the vibration that we measure from there to check whether we can use that vibration signal as in our quality management in our quality gate. So that is our objective. However, in the actual productions, the quality will check about for hole drilling process. They will check whether the holes the amount of holes drilled are correct. They will check also whether the position of the holes are correct. They will also check whether the diameter of the holes are correct. So these three things. So but since this is our let's say that our first exploration into this into vibration analysis of a pneumatic rig gun and coupled with the manual process, so we're gonna limit it into on only the first item. We're gonna segregate the signal, and we're gonna identify the signal to see whether we can identify any signature pattern that could be associated with the drilling action of the operator. So if the signal occurs, then we know, okay, this is when the hole has been drilled. Okay, this is not. And then this is how we build our sensors, our device. The sensor that we are using is inertial measurement unit, or IMU. Inside here, it is consists of 3 different sensors actually. It has accelerometer, gyroscope, and magnetometer. And luckily, we have found a microcontroller unit called Arduino Nano 33BLE Sense. The IMU is built into it. So the reason why we are using Arduino Nano is that because it also has built-in embedded into it is a Bluetooth module. Why we want to use Bluetooth module? Because let me stress again that this process, this project is done in the industry. So what we're gonna do is that we're gonna measure the actual vibration done by the operator in the shop floor condition. So we cannot have wires dangling around in the shop floor. It's gonna disrupt the process and everything. That's why we use a Bluetooth module to communicate with our Raspberry Pi model. This is our processing unit to do the analysis. Okay. The reason why I'm also choosing Raspberry Pi is for me for us to control the cost to not because Arduino Nano plus Raspberry Pi both of them are inclusive of the other the display unit, all the wires and everything. It costs less than 1,000 ringgit. So compare it to the cost of having to build a new jig and everything for machine is very far. So and then we think that the cost is deemed acceptable within the industry. And then this is the completed device. You can see that there are no wires. Everything is the communication is done through Bluetooth. And then the sensors, the Arduino Nano with the IMU embedded is located inside this makeshift hole. And then it is powered by 3.3 volt lithium-ion battery. That is also the advantages of using Arduino. So what we're gonna do is that we give the operators, instead of using their usual drill gun, we give them this drill gun, and then for them to do the actual process onto the actual panel. So the data that we get is real. It's not experimental data. It's not analytical data. It is the actual real data from the actual real shop floor doing the actual real panel. So based on the IMU, we get nine values. The first values are from accelerometer, the triaxial expression in X, Y, and Z. Rotational speeds from gyroscope in X, Y, and Z. Also magnetic fields from magnetometer in X, Y, and Z. Surprisingly enough, out of this 9, only one exists. One set of data can be used. The rest are either too erratic, either too noisy, cannot be fitted and everything. Only one can be used. And then that one is acceleration in X direction, the sideways direction of the drill gun. And then this is the example of how the data looks like. And then this is the manual labeling that we did in order for in our initial analysis of the data. So we label the whole. It is plotted in time domain measured in milliseconds. So for this specific process, there are 12 holes drills with some noise in front. So the first question that you're gonna that we want the signal to give us is when the hole has been drilled. So in order to answer this question, we cannot rely on Fourier transform. So because Fourier transform is just gonna give us some frequency data, it cannot give us when the frequency has been used. That's why, as alternative, I'm using wavelet transform, in specifically continuous wavelet transform, in order to give us the view in time domain instead of in frequency domain. So the difference between wavelet theorems and Fourier theorem is that Fourier transform they use an infinite amount of sine wave. However, for wavelet transform, it use a different kind of wave called wavelets. And for this specific analysis, I'm using wavelets called Mottlet wavelet. And then it is finite. At any single point of time, only one wavelet exists in the analysis. So I'm going to multiply this wavelet into the expression value in acceleration using this using the continuous wavelet transform formula. So this is the result that I get. Result that I get is in matrix. The value are called coefficients. So and then it has to be at different scale. So instead of portraying all the numbers, I'm changing it into a scalelogram. This is called a scalelogram. In order to ease the visualization of the result. So this is the scale of the scalelogram, the value of the coefficient at specific scale. So what scale scale is the measurement of the wavelet being stretched. This is scale 1 at default length. Scale 2 when the wavelet is being stretched further. Scale 3 is even further. The higher scale is, the further it is being stretched. The wavelet. So one thing that we need to understand is that this term here, the underlined in red, known as scale factor, and then according to FAKE 2020, it is inversely proportional to frequency, which means that the lower scale corresponds to the highest frequency. And then the statement is true because we can see here in this scalelogram, there is a concentration of high value of coefficient, and it corresponds to the same value in at the same time that there is a vibration of the whole direction drill of the whole. So it corresponds to the same time. And then since we know that the lowest scale corresponds to the highest frequency, so I'm just gonna I'm gonna take the value at scale equals to 1. So this is the value of coefficient at scale equal to 1. So I'm gonna use it for to further further analyze and to check whether we can see when the drill has been drilled using this data.
Mr. Vidas, can you sum up your presentation in 1 minute?
Oh, sorry. Okay. Thank you, Dr. Haris. Okay. Basically, based on the continuous value transform, we have done the analysis and everything. But the analysis, there are a few. They will be in 4 situations. Whether we have a true reading, whether it is undercounted, overcounted, and also false positive. False positive is when it counted correctly. Let's say that we have 12 holes and it counted 12. However, that 12 that we counted, because there is over detection and under detection inside the same appear inside the same signals. So we call it a false positive, because even though the amount counted is correct, but the signal that they count are wrong. So in order to increase the accuracy, I move into a classification algorithm. I'm using a decision tree, and then we managed to increase the accuracy from 28% to 70%. Even though the accuracy is maybe 70% is not that high. However, we managed to eliminate totally over detection. So all the detection done are all signals. We can say that can be associated with the drilling action. There are no noise inside the correctly counted signals. And for conclusion, based on the activity that we have done, we have seen that the vibrational signal generated are random and very chaotic. Okay, this is we say it is to be expected because we are dealing with the manual drilling process. And we have seen we have throughout the process, based on the result also, we have seen that it is actually feasible, probable, practical, in order for us to use the vibration signal measured using accelerometer in our quality control gate. So probably we're gonna propose this to the industry for actual application.
Okay, then I think that's all, Mr. Firdaus. Thank you very much for your presentation. So maybe I just open only maybe one question to Mr. Firdaus. So from any from audience, do you have any question to ask? I can open only one question.
Can I ask one question?
Yes, please.
Okay, maybe it's not very related to your scope of the project, but I'm quite interested in the process of hand layup. So now we are in the 20th century with the IR 4.0, everything. Is there any recent progress on the process related to the hand layup? Maybe it's a more automated process in the aerospace industry.
Because when we want to say automated process, right now the biggest hurdle is the material itself, because why we have to do hand layup, because we are using a woven fabric. So most of the automated, let's say that AFP or ATL automated tabling are using UD materials. So for UD, it is easier for us to do the automation. But for fabric materials right now in the industry, there are no automation yet.
Yes, I can agree with you. But I think there's a recent progress, I think, in UK, where they're currently developing a automation process replacing the hand layup, proof of concept. I think it's quite recent.
May I know what's the name of the
I think it's a Bristol University. If you might Google later.
the name of the process
I'm,
the
I'm,
machine
I'm not. It's not yet commercialized. It's in the proof of concept stage yet.
I see.
Okay, all right. I think thank you very much. Okay, thank you very much for the second presenter, Muhammad Firdaus. So I return back to the second presenter, second paper of this session. Mr. Linus, are you there? Mr. Linus?
Oh, hello, can you
Yes,
hear me
Mr.
over there?
Linus. Yes, yes.
Okay, okay, sir. Okay, sir.
Okay, Mr. Linus, you can present your work.
Okay, thank you very much. The session chair, Dr. Mohammed Nasir. I'm presenting from Nigeria. Good morning, everybody. It's morning in Nigeria. What I discovered that in Malaysia, it's afternoon now.
Yes, exactly. Yes.
Okay, thank you very much.
So, are you using two devices? Maybe you can switch off the other one.
No. It's only one device. Okay. Yes. I hope the other one.
Okay.
Thank you.
Please. Okay. Please proceed with your presentation.
Okay. I have 20 minutes presentation. I'll
Yeah,
try as
10
much
to
as
15
possible
minutes. Yes.
to meet up with time.
All right.
Thank you. I'm Engineer Sadachi, Department Mechanical Engineering Department, Air Force Institute of Technology, Kaduna, Nigeria. Paper title: Performance Analysis of Yellow Hollander Seed Oil Biodiesel Power Aeroderivative Gas Turbine Engine. Outline: Overview of gas turbine. Background of study. Aim and objectives. Significance, scope, material deployed, method, result and discussion. Finally, conclusion. What is gas turbine? Gas turbine is a steady flow continuous combustion internal combustion engine. Consists essentially of one compressor, combustion chamber, turbine. Field of application. That is area of application. One, in aviation. In aviation, it can be civil and military. Then, power generation, industrial, that is land-based. Oil and gas pipeline pumping system, marine, Marine could be C proportion, that is civil and military, and gas offshore platform. This is a model aviation gas turbine. You can look of air where the compressor ram the air into the compressor, and you see combustion chamber where the mixture got born, and the 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 exhaust turn the turbine blade, and essentially here what we want here is a thrust power. Sorry, this is a land-based gas turbine. You can see they're almost the same, but difference between here is shaft power, where it rotates the generator and bring about power. Gas turbine fuel. Gas turbine can use variety of fuel. The usage depends on application. Could be liquid fuel, that is kerosene, can be diesel, heavy residue grade, oil and crude oil, then biodiesel, which is alternative and renewable, etc. It could be gaseous fuel, that is, it could be natural gas, propane, cook gas, coal gas, and biogas, alternative, etc. Cycle configuration. The thermodynamic cycle name gas turbine is Brayton cycle. Constant pressure will be simple open cycle, regenerative cycle, intercooled cycle, heat cycle, combined cycle, cogeneration, or combined heat and power. Lastly, integrated combined gasification cycle. Background of study. Gas turbines are used as simple open cycle and combined cycle. Configuration in Nigeria. Fuel use could be natural gas, mostly because of its availability, not applicable in aero engine operation. Issue in natural gas: environmental concern, emission, depletion of natural reserve, fluid nature of supply to power station, statement of problem. The following statement of problem can be looked upon: soaring pump price, increase in energy demand, depleting reserve, strict emission regulation, national biofuel policy, etc. Gas turbine are fossil fuel. So because a suitable alternative, because it is a similar physicochemical property with conventional diesel. However, it is important to assess the performance of gas turbine while operating with biodiesel to mitigate emission and lift challenges. The aim of this research, the aim of the study is to carry out performance analysis of Hollandaise biodiesel when used to power derivative gas turbine engine. So the objectives of this study to investigate the physicochemical property of yellow Hollandaise oil biodiesel and some of its blend with conventional diesel for use in gas turbine. Second, to simulate the performance of of an electrolytic turbine engine when powered by yellow or landed biodiesel through the use of gas top software. Lastly, to compare the performance in terms of the variation in specific fuel consumption, power output, mass flow, thermal efficiency, and level of pollutant emission. Significance of the study. 1. The promotion of alternative renewable for powering gas turbine in power generation industry. Locally sourced biodiesel are expected impact on domestic economic activities. Third, the achievement of environmental friendly operation of our thermal plant nationwide. Finally, operationability of the investigated engine with the biodiesel fuel. Material deployed for this research: fuel blend B10. That means the biodiesel is 10%, conventional diesel is 90%. B20, biodiesel 20%, conventional diesel 80%. B30, biodiesel 30%, conventional diesel 70%. B40, biodiesel 40%, conventional diesel 60%. Lastly, B100, that's 100% biodiesel. Simulation tools, gas top 13, Microsoft Excel 213. The technical specification of the baseline gas turbine LM 2500. Technical specification of the baseline engine. That's performance parameter. 1. Power output 25 megawatts. 2. Combustion pressure loss 5. Turbine isentropic efficiency 0.9. Turbine inlet temperature 1505.5 Kelvin 5. Compressor isentropic efficiency 0.876. Pressure ratio 18.75. Air mass flow 72.5 kilogram per second. Method. The method for this research includes production and characterization of biodiesel fuel blend, modeling and simulation of the thermodynamic cycle based on the GLLM 2500. Physicochemical property of the biodiesel blend. It is produced and characterized at National Research Institute of Chemical Technology, NIRE, Zaria, Kaduna, Nigeria. The properties, which include flash point, pour point, calorific value, specific gravity, viscosity, density, etc. Based on ASTM standard specification, which is stated here, result and discussion. The result is discussion based on the chemical property of the investigated fuel. Second, of design performance. You can look for the grants, variation of specific fuel consumption for different fuel blend. Yes, you can see that B100 has higher specific fuel consumption compared to B0, which is conventional diesel, meaning you have power output. Second result, variation of power output. We have B0, which is conventional diesel, have lowest power output, and have B100, which is biodiesel, have higher fire because you have higher specific consumption, which is directly proportional to the mass flow. The variation of fuel mass flow, as earlier stated, mass flow is tied to specific fuel consumption. The higher the mass flow, the higher the specific fuel consumption, and the higher the power output. B100 have a higher fuel mass flow, meaning it produce higher power output. Variation of thermal efficiency.
Sorry, Mr. Linus, can you sum up your presentation in 1 minute, or just discuss about your main findings?
Okay, sir.
All right.
So, in conclusion, the physiochemical properties of the investigated biodiesel blend were found comparable with that of ASM standard specification. The NOx emission obtained was 0.2628 for all the fuel. Lastly, yellow Hollander biodiesel and its blend were found to compete favorably well with this reference fuel, diesel. Therefore, it can be suitable replacement for diesel fuel. Performance. The gas turbine engine investigated generated the most power while firing with the diesel and their blend. Yellow Hollander biodiesel have a higher power output compared to diesel fuel at the expense of higher mass flow rate. Recommendation. The effect of higher blend on the performance of the investigated engine be explored. The performance of engine be carried out under transit conditions. A assessment of body be conducted. The commercialization of the biodiesel to be encouraged. Recommended of B5 to B20 of the biodiesel policy for commercialization. B5 to B20 grade biodiesel will be implemented. Thank you.
Okay, thank you very much, Mr. Linus. So maybe I just open one question. Any question from the audience to ask Mr. Linus?
Yeah, just one thing to ask. What is the unit of the what they call it NOx that you mentioned just now? 0.50. Is it a ppm or gram per kilogram of fuel? What is it?
However, positive CL at 2 degree was experienced until 8 degree, but it lasts for a short period of time.
I can't hear you very well.
Global and unstable onwards. In short,
Linus, can you give me the unit that you obtain for the NOx? 0.502 something. Is it in term of ppm or is it in term of gram per kilogram of fuel? What is it? What is the unit?
No, there's no unit. The network is tracking. I'm not hearing well. But based on what I said, The 0.52 is what I deduced my finding, and is constant throughout the fuel.
Thank you very much, Mr. Linus. Maybe Mr. Hanafi, if you have any more questions, you can contact personally to Mr. Linus to discuss. So I'm going to proceed with another presentation for the number 4 in this session. So I would like to call upon presenter the paper entitled Addition Durability of Metal Epoxy Adhesively Bonded Under Tropical Weathering Exposure. I'm sorry. Number 4 is optimization of the combustion performance when firing waste cooking oil biodiesel plants in a liquid fuel burner. Okay, the authors are Muhammad Shahiran, Muhammad Nazri, Muhammad Jaafar, Nur Razila, Muhammad Suisma, Muhammad Roslan Narhir, and Mazlan Said. So any representative from this paper? Paper number 4, optimization of the combustion performance when firing waste cooking oil biodiesel blends in liquid fuel burner. Okay, so I believe Shahiran, I'm going to present it.
Hello.
Yes, Shahiran.
Yeah, I'm going to present this
Can you
paper.
speak louder, Shahiran? We cannot hear you, your voice.
I will presenting this paper.
Okay, you can share your slide.
Okay, wait a minute.
Okay, Shahiran, you can start now.
Assalamualaikum and very good evening to the chairman, presenters, and to the participants. I am Muhammad Shahiran Abdul Malik from the School of Mechanical Engineering, UTM. Would like to present our research on optimization on the combustion performance when firing with cooking oil biodiesel blend in a liquid fuel burner. I begin my presentation with a brief background of this research. Waste cooking oil is an oil that repeatedly used for frying during food preparation. It is estimated about 20 million tons of this oil abundant around the world. Because of this, the oil is discarded improperly and do cause harmful effects to the environment. Besides that, the repeated usage of this oil do cause harmful to the human. Despite all this danger, this oil has the potential to be converted to biodiesel using the current esterification process for alternative industrial fuel. Biodiesel, which is a clean and renewable fuel, can be derived from edible or non-edible feedstock through the reaction with alcohol in the heat of catalyst to gain alkyl ester as the fuel and glycerol as the waste product that can be used for other products such as soaps and skincare products. RSM, the research surface methodology, is a statistical method applying regression model to assess the effect of the system factors to the response and estimate the outcome of the response from the system factors. The optimization of RSM has been applied in biofuel research to maximize the fuel production, improve fuel physical properties, and maximize the engine performance and reduce emissions. Next is the gap of this research. Liquid fuel burner is a mechanical equipment that fires the mixture of fuel and air in a combustion chamber to generate heat energy for industrial application. The research of utilizing edible and non-edible biodiesel in the liquid fuel burner has been done by many researchers. They found out that varying the equivalent ratio P and the percentage of biodiesel blend affect the combustion temperature, nitrogen oxide, the NOx, and carbon monoxide CO formation. As what can be seen in the figure, that progressing the combustion from the lean fuel to stoichiometry will increase the combustion temperature, NOx, to its peak, while CO is reduced to its lowest point. As the combustion progresses further, the combustion temperature will increase to reach its peak. Before drop, NOx will progress to drop and CO will increase to reach higher value. As for the biodiesel blend, low blend will have high values of the combustion temperature, NOx and CO, while high biodiesel blend will produce the value of graduate. As from this characteristic, it is difficult to gain high combustion temperature while keeping low formation of NOx and CO. Thus, the aim of this research is to optimize the combustion of WCO and E with cooking oil methyl ester by combustion using RSM, high combustion temperature and low formation of NOx and CO.
Of the registration of engineers.
Next, I will briefly explain how the process of this research.
Amendment Act
In this graphical flow chart, the filtered waste cooking oil from various vegetable oil sources was filtered and mixed with methanol and EOH at 6:1 molar ratio and 1.3% weightage of potassium hydroxide KOH. The mixture was poured inside the glass reactor, stirred and heated at constant temperature for 1 hour. After that, the mixture was transferred through the separation funnel to allow the separation between waste cooking oil methyl ester, WCONE, and glycerol. WCONE was then taken out and washed with distilled water until the washing water becomes clear. And finally, WCONE was heated to remove any remaining water and let to cool down before blending with conventional diesel fuel CDF to produce D10, D30, and finally D50. Next is the setup for the liquid fuel burner. First, the fuel was pumped into the BTL 10 industrial fuel burner and atomized to fine droplets using the D11 type W nozzle. The atomized fuel was mixed with air from the burner blower and ignited using the burner igniter. The flame and exhaust gas generated from the fuel combustion was contained inside the concentric cylindrical combustion chamber. One type A thermocouple was put at the end of the combustion chamber to detect the exhaust gas temperature. The exhaust gas then was channeled into the gas chamber and flowed through the gas transfer to detect the NOx and CO concentration before expelled out from the combustion room using the exhaust tank. Next is the experimental metric to perform RSM optimization. the WCOMe biodiesel blend from B10 to B50 and the equivalent ratio C from 0.8 to 1.4 were considered as the combustion factors, and the exhaust gas temperature, NOx and CO, were the response from the combustion. The Central Composite Phase Center CPFC design model was applied in RFM using the Design Expert Software version 10 and generated 11 randomized experimental runs to perform this experiment. Next is the result and discussion. The result of the research are shown in the graphical plot, which is the predicted versus actual graph, and response plot, which is the contour and surface plot. The predicted versus actual plot is shown to show the relationship between the predicted and actual data. The contour and surface plot are the predicted plot of the regression model that show the strength interaction between the factor and responses. There are 4 color indicators, which is red, yellow, green, and blue that used in the response plot to show the intensity of response from the effect of the factor. The predicted versus actual graph for the exhaust gas temperature, NOx, and CO are shown in this slide. From this plot, it can be seen that most actual and predicted data are close to the regression line. The value of the coefficient of determination, R squared, and adjusted R squared are close to one another. The value of the predicted R squared do not exceed the standard RSM limitation of 0.2, different from R squared. From this plot, it can be concluded that the regression model had good fit and predictive quality on estimating data close to the actual. Next is the contour and surface plot for exhaust gas temperature. It can be seen that the interaction between C and WCO and E blends do not show good interaction to one another from the multiple linear lines in the contour. Good interaction is shown by the elliptical curvature lines at the red region concentrated at C 0.9 to 1.1 and along the WCO and E blend. Because of high fuel supply and enough air that promotes high temperature combustion, the temperature at this region is between 836 to 858 degrees Celsius. The temperature is around 800 to 820 degrees Celsius from 0.8 to 0.9 along WCO and E blends due to lower release from the fuel combustion in excess air. Great reduction of temperature to 760 degrees Celsius is seen when C progress later than 1.1 due to great air supply reduction that restricts the fuel combustion. Next is the contour and surface plot for NOx. Multiple elliptical curves can be seen from the contour plot, which indicate excellent interaction between C and WCO and E blends. High value of NOx between 58 to 59 ppm can be seen between WCO at E, B10, and for 250 and C at 0.9 to 1.15. This is indicated by the red yellowish color region. Increasing WCO and E blends to B50 will not much affect the NOx formation at low value of P but reduce to 45 ppm at high value of P due to lower energy content in the fuel and air supply that restrict the formation of NOx. As for increasing the value of P, emission will slightly increase to its peak and then reduce to 45 ppm as P progress to 1.4. This is due to the effect of thermal NOx that rely on combustion temperature and the presence of oxygen. Next is the contour and surface plot for CO. Multiple elliptical curvature lines can be seen between 0.8 to 1.4 to the ratio, and P straight line when P is higher than 1.2. The low value of CO from 0 to 18 ppm is seen to concentrate almost half of the plot until P 1.1 and along WCO&E blends. This is indicated by the blue color region. Such low CO is due to the presence of enough oxygen that promotes complete combustion, thus lowering the CO formation. Increasing P will increase CO to 300 ppm due to the reduction of oxygen that causes incomplete combustion, and increasing WCO&E will slightly increase CO emission at low P due to the existence of several improper mixing regions from greater kinematic viscosity of the biodiesel fuel that restricts fine fuel optimization. Next is the RSM optimization solution for WCO&E combustion. RSM suggests multiple solutions for the optimization, and the best three solutions is shown in the table. The three solutions were set and combusted to verify with the actual experimental data. It was found out that solution number 1 is the closest to the actual experimental data in number 1, while solution number 2 and number 3 experience much different in CO and exhaust gas temperature with the actual data. Last is the conclusion of this research. It can be concluded that the utilization of RSM optimization solution able to set appropriate WCO&E blends of B28 and C at 0.82 to keep high combustion temperature of 803.4 degrees Celsius and low NOx and CO formation of 52 ppm and 13 ppm. That's all from me. Thank you for your time.
Thank you very much, Mr. Shahiran, for your presentation. So now I would like to open one or two questions from the audience. If anyone would like to ask any question to Mr. Shahiran. Okay, any questions from the audience? Okay, so I think it's no question from the audience, so meaning that everyone is understand your presentation. So thank you very much, Mr. Shahiran, for your time to present your works.
Yeah, thank you for the presentation opportunity.
All right. Okay, so now I would like to call presenter from paper number 5 from this session. It's entitled Addition Durability of Metal Epoxy Adhesively Bonded Under Tropical Weathering Exposure. And the authors are Nur Ashikin, Muhammad Airul Amin, Mahzan Johar, and Syukur Abu Hassan. Mr. Shahiran, can you please unshare your presentation?
Sorry, but how to unshare?
I think you can just close your presentation. Okay, just click cancel.
I'm sorry, but can I just
Can you click share there over there, the button share, then cancel there?
then
Or is it share constant?
Tengok. Syarah, tengok taskbar kat atas tu. Taskbar yang warna orange tu kat atas sekali. Lalukan cursor kat atas tu.
oh dia macam ni.
Ya, kat
Okay,
situ.
okay.
Yes, yes.
Sorry.
Stop sharing, yeah, please.
Daripada Viber tak pergi.
Okay, I think now I will call upon Nora Shikin to present her works entitled Addition Durability of Metal Epoxy Adhesively Bonded Under Tropical Weathering Exposure. Okay. Waalaikumsalam. Okay, Nora Shikin, can you share, can you make it presentation mode, your screen?
My name is Nur Ashikin from School of Mechanical UTM. Paper is collaborative work between Mama Aira Amin and Dr. Syukur bin Abu Hassan from Center of Advanced Composite Materials UTM. Today I perform this presentation about a study titled of Adhesion Durability of Metal Epoxy Adhesively Bonded Under Tropical Weathering Exposure. So as introduction, have three method of joint technique, which are mechanical fastening, fusion bonding, and adhesive bonding. And here I chose epoxy as method for this study. But have advantage and limitation for adhesive bonding versus the joint technique. Which is the advance of the adhesive bonding is inexpensive, short process time, uniform stress across bonded surface, and flexibility in assembly process and load configuration, and wide design and material option. But the limitation is the surface preparation is needed, adhesion degradation due to environmental factor, and possibility sensitive to environment, service temperature are limited, and inspection of bonded joint is difficult. About tropical exposure weathering, this adhesive have degradation due to outdoor exposure. This study examined the effect of tropical weathering on deformation and mechanical properties of steel and epoxy joint. Adhesive bond lead to a wide application in all the sectors such as aerospace, automotive, marine, sport industry, and even in the civil construction. Composite structure in severe experience damage that come from the accidental impact and mechanical or environmental condition. The main environmental threats are related to the effects of temperature and moisture absorption, which can affect the strength of structure and reduce their service. Characteristics of Malaysia climate are that it has a uniform temperature, high humidity, and abundant rainfall. Temperature and moisture levels could vary throughout the day. The cycle temperature and moisture could even further the structure and then lead to premature failure of the structure. This graph figure 1 daily air temperature and relative humidity variation in Johor Bahru for 12 June 2020. Show the cyclic temperature and moisture for every introduction type of joint failure. We have 6 types of joint failure. Adhesive failure, which is the adhesive in the face. Adhesive failure, thin layer adhesive failure, fiber tear failure, like fiber failure, break failure. In evaluating an adhesive joint performance, physical or chemical properties of the adhesive used are the most important factors, which bond strength, structural integrity and durability are to be evaluated. While the strength and durability is influenced by adhesive properties, adherence type, surface pretreatment, and joint configuration. Take note, suitable design and parameters need to be evaluated to prevent low load carrying capacity or over design. This project aim is to evaluate the mechanical degradation of steel and epoxy joints subjected to tropical weathering exposure. Objective, we have 3 objectives here is to evaluate the adhesive joint strength degradation after exposure when subject to different configuration. Analyze the effect of tropical exposure on each stress component during peak load, and to calculate the stress energy density variation due to tropical exposure. Our scope is based on some boundaries and assumptions underlined during literature review process, and material selection and joint configuration were decided based on cost and complexity constraint and also application in the industrial world. The conclusion was discussion and explained in detail in next page. And the failure mode were observed on the post-failure sample. Research methodology, which is material is steel, big 30 times 30 size. We have adhesive 1 mm. Control use plastic slice 1 mm. Area of the adhesive is 5 mm diameter. Sample after prepared. Face roughness goes by sandblasted with silicon carbide with grid size number 200 is 0.0025 inch to produce surface roughness with a of 50 micron. Acetone applied to remove impurities on the surface. Further 330 epoxy was applied to the steel bonded surface using hand brush technique. All those samples, we have 2 sample group were made, which is control outdoor. Is TRL and OTDR. Left out with after 24 hours in room temperature. Control sample were directly tested after cured, and outdoor samples were exposed to outdoor environment for 170 days. Cyclic temperature and moisture. At tapak uji kaji penyelidikan bahan struktur UTM. This location is in the After this, for the rest topic of this presentation, I will pass to Mr. Airul Amin.
Okay, Assalamualaikum. I will continue for the research methodology. Okay. So, the modified Akanji was attached to the universal tensile machine, and the loading rate used was 1 millimeter per minute.
Errol, can you please turn it into presentation mode?
I already turned into presentation mode.
Okay, so
Okay.
okay, maybe just carry on. Okay, please.
Okay. So this modified Akanji enable different orientation angle to be used in the loading configuration. So in the study, we use 3 different loading configuration: 90-degree, or pure tensile, 45-degree, and also 0-degree loading configuration, which is pure shear. And then the load displacement response were recorded for the whole test until failure occurred. Since the adhesive and the adhesion properties are considered homogeneous, so plane stress conditions are considered for the adhesive. Therefore, the applied load can be resolved into two stress components, namely normal and shear, which is represented by the equation at the right of the screen. Then adding the significant area into the equation, we can get the average normal and shear stress described by the equation as shown at the bottom right of the screen.
I will enable editing, then full screen.
Sorry?
Enable editing.
I think your presentation you have to do it again. Open the enable editing and then click the.
Okay. Sorry. Is it okay now?
Okay, now okay.
Okay.
Please carry on.
Yeah. Moving to result and discussion. Since most epoxy adhesive are brittle in characteristic, its load displacement response of when applied to the adhesive joint also follow the brittle behavior. And Cicado 330 also is not an exception. Therefore, as we can see from the graph at the left of the screen, only 2 sections can be highlighted in the load displacement curve. First is the linear elastic region, at which homogeneous deformation of adhesive occurs until peak load, and then the post-fracture region, in which total separations occurs immediately after crack initiation during peak load. The graph on the left screen, the graph on the left of the screen show the load displacement response for the control samples at all loading configuration. From the graph, you can see that higher peak load and elastic modulus are obtained during pure shear configuration, while larger maximum displacement can be seen during pure tensile configuration. This each configuration, this load displacement response is then compared to their respective outdoor sample, as shown by the 3 graphs at the right of the screen. From the graph, you can see that major strength degradation occurs on all of 3 configuration samples, signified by the maximum load decrement and also the shear strength decrement. The value can be seen in the table below the screen. However, for elastic value, only small difference is observed in the pure tensile and combined loading configuration, while massive 55% decrement is observed for the pure shear configuration. The maximum displacement of all the sample also much lower compared to their respective control sample. The major reduction of shear properties after exposure also can be discussed by the stress components radiation acting during peak load. As noted in the graph shown at the screen, wider difference of stress value can be seen as the configuration move toward shear dominant loading configuration. The stress and difference in value can be seen in the table below. At the combined loading configuration, which is 45 degree, by comparing the stress value to its respective principal stress, it can be concluded that the failure of the control specimen of 45-degree loading configuration is tensile dominant, while the outdoor specimen for 45-degree loading configuration is shear dominant. Other than that, the performance of the adhesive joint also can be evaluated by the strain energy density value. The strain energy density is defined by the relation between the energy employed to deform a unit volume of solid and imposed strain. So as discussed in the load displacement response before, major shear properties reduction heavily affected the performance of the outdoor samples. This can be seen by the 95% stress energy density value reduction during pure shear configuration compared to only 28% during pure tensile configuration. Since the outdoor sample for 45-degree configuration is shear dominant in failure, so high degradation value also obtained for the stress energy density value. The post-fracture observation also done to all the samples. The two picture at the bottom right of the screen show that the post-fracture sample of the 45 and 90-degree loading orientation for control sample and also outdoor sample. Based on the observation, we can see that there is mixed failure occur on both samples, which mixing of the adhesion failure and also cohesive failure.
Okay, Errol, sorry, can you please sum up your presentation?
Okay. While for the zero loading orientation, only adhesion failure observed. So in conclusion, based on the objective outlined before, we can conclude that the mechanical properties of the adhesive joint was compromised due to tropical weathering exposure. This is signified by the large degradation occurs, particularly at the shear dominant configuration, in which the mechanical properties value decrement value are mentioned at the screen. And then adhesive joint shear stress component is heavily affected by the tropical weathering exposure. This is shown by the largest stress value difference between control and outdoor sample at peak load during pure shear configuration compared to tensile. And also at the combined loading, where the outdoor sample more shear dominant. And then the strain energy density value of the outdoor sample heavily decreased with 95% at the pure shear compared to 28% at the pure tensile. And lastly, based on the observation, adhesion failure was observed for both control and outdoor sample when subjected to pure tensile, while mixture of adhesion and cohesive when subjected to combined and pure shear. From this, we can conclude that samples are more vulnerable to adhesion failure during tensile dominant loading configuration. And as an acknowledgement, we are thanks to the University Technology Malaysia and also CRG National Grant for this project. Thank you.
Okay, thank you very much. Sorry, I mute just now. So, any question? Maybe one question from the audience.
Maybe a quick question from me. Thanks for the presentation. How do you identify between the adhesion and cohesive failure mode? Is it through visual inspection?
Yes. Through visual inspection.
What's the difference?
Sorry?
What's the difference between the adhesive and cohesive failure?
The adhesion failure, the failure occurs at the interface, means between the epoxy and the metal surface. While for cohesive failure, the failure occurs inside the adhesive itself. So in the observation, for cohesive failure, you can see the adhesive at the both sides of the steel sample, steel adherent. Okay.
Thanks.
Okay. Okay, Airul, thank you very much for your presentation, as well as Nur Ashikin. All right, please, Airul, please stop sharing your slide.
Okay, thank you, Dr. Haris.
Sama. All right, so now I would like to call Shahiran. Shahiran, still you didn't stop your slide. Mr. Shahiran, can. Okay. By the way, we proceed with the next presenter. The paper entitled CFD Analysis of Rocket Convergence, Divergence Nozzle with Swirl Vanes for Improved Stability. The authors of this paper are Ahmad Hussein bin Abdul Hamid, Akmal Nur Ashikin binti Omar, Zuraidah Saleh, Muhammad Joini Sujana, Muhammad Amirul Muhammad, Muhammad Shahar Saad, dan Muhammad Ismail Kamis. So any representative from this paper? Okay. So Ahmad Hussein, you can start your presentation. Please open your slide to the presentation mode.
Okay, sorry, I'm struggling with finding the microphone.
Okay, all right.
Okay.
Okay, please proceed.
Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Okay, so first of all, thank you for the opportunity. So I'm going to present the research title, CFD Analysis of Rocket Converging Divergent Nozzle with Swirl Vanes for Improved Stability. So basically, this work is in a collaborative efforts between School of Mechanical Engineering, UiTM, under the lab HEMREL, and also with the MTC Defense Niam Berhad. Basically, rocket consists of a few major components, including the nose cone. Okay. Okay, the nose cone, and then the body itself. Okay, which is enclosed by the case, and also the nozzle. Okay. So our focus in this project is on the nozzle itself. Basically, the rocket nozzle has three major roles. First is to control the combustion pressure through the adjustment of the throat size. Okay, basically we have to determine what is the pressure required to gain the certain thrust. And the second function of nozzle is to accelerate the combustion gases through the diverging section of the nozzle. So it is very crucial to ensure that the gas flows through the throat at a sonic flow, so that it can be further accelerated to a supersonic condition at the diverging part of the nozzle. And finally, the main function of nozzle is to provide flight stability and control. Okay, so our main focus in this research is to use the nozzle to provide the flight stability and control. So when we talk about flight stability, okay, we have to see the aerodynamics of the rocket. So basically, the rocket aerodynamics is the study of how air flows over the rocket and how it is affect the drag and also the stability of the rocket. In general, the rule of thumb is that if you have the center of pressure to be located lower than the center of mass, the rocket is deemed to be stable. Okay, so if you look at this, the second figure, okay, due to the certain condition, the rocket tends to sway to the certain angle, or known as the displacement angle. Okay, so if the center of pressure located below the center of mass, okay, the aerodynamic forces, which can be decomposed into the lift and drag component, will produce a restoring torque about the center of mass, and this will restore the position of the position of the rocket, so that the axis is aligned to the direction of the motion. Otherwise, if the center of pressure is located above the center of mass, okay, so the aerodynamic force will produce a destabilizing torque about the center of mass. Okay. Now, how do we achieve stability in rocket flight? Okay, there are few ways, but the first one is through fins, and there are many fins parameters. Okay, for example, here we have the root and tip chord. Okay, so bear in mind, okay, the general idea is we can increase the stability of the rocket by increasing the size of the fin. However, by increasing the size of the fin, we also increase the drag of the rocket. So there is always a competition between the stability and also the efficiency of the rocket flight. The other second parameter is the fin cant. We can also vary with the fin cant angle, and also the fin planform, the fin sweep, and also we can play around with the number of fins. Okay, so but this is not our main focus in this study. Another way to achieve stability is through the spin stabilization. Okay, so basically in spin stabilization, okay, the rocket can go further from the unstable rocket. So how do we achieve spin? There are a few ways. One is through the launcher itself. Okay, this is an example of helical launch tower. Okay, the rocket can also be spun through a fin. Okay, so we have a few types of fin. So here we have a folding fin. So we have a wrap around fin here. Okay, so this type of fins can also induce a spinning motion of the rocket. And last one, we can also induce the spinning through the nozzle itself. Okay, so this is our main focus of the study. So as can be seen here, okay, this is a nozzle with a swirler here, and also we have a nozzle with fluids. Okay, so basically there are two major types of nozzle used here. So it has the nozzle incorporated with swirler, okay, will impart torque to the rocket, and thus the rocket will spin. Okay, and there are various parameters as well in this design. For example, is the number of fluids or swirl vanes, okay, and also the height of the swirl vanes, okay, and also the number of fins. So you can see here that there are 4 fins in this Korean 2.75-inch rocket, and there are 3 fins here for the MK66 rocket nozzle. All right. So it has been shown, okay, in the previous study, Maya et al. In 1996, okay, that the number of vanes severely affect the torque produced, okay, on the rocket. Initially, the author anticipated that the highest torque value would be generated by the motors with the greatest number of vanes. However, okay, they found that the motor with the least number of vanes, okay, for example here the 9 with this one, the indicated by the dash lines, produce the highest torque levels as compared to the highest number of veins, which produce the lowest top. Okay, so they argued that the flow separation from the adjacent upstream veins are responsible for this degradation of the top produced by the most number of veins nozzle. Okay, so when the adjacent upstream veins were removed, the flow separation was avoided, and hence the efficiency of the remaining veins improved. Okay, so the benefits of having smaller number of veins, first, they improve the specific impulse by increasing the effectiveness nozzle expansion ratio. Secondly, it reduces the shock. And lastly, it reduces the skin friction losses. Okay. It is also important to note that these swirl veins also produce two additional effects. The first one is they increase the burn rate of the solid propellant. And they also cause a slight decrease in pressure in the flow field due to the swirl. Now, the objective of this study is to establish CFD method as a technically viable and less expensive alternative to experimental testing, to validate an open source solver with published data, to conduct preliminary analysis of a nozzle with swirl veins. The first step is to select the appropriate solver and boundary conditions. In this particular study, we use a density-based solver known as a row central foam. And it is most important to select appropriate boundary condition for the outlet boundary to allow a smooth transition of shock wave through the boundary. So we don't want any reflective shock wave near the exit boundary. So for this particular case, we use wave transmissive outlet boundary condition, and the pressure and temperature of the combustion is simulated using the AP-based propellant with initial combustion pressure of 500 psi or 34.47 bar. Next, once we have set the boundary condition and the solver, we then run a solver validation. And once validated, we then construct the nozzle and the numerical domain. We did a grid independent study and numerical analysis of the base case. Okay, so it is important to note that in this project, we have divided into two phases. So the first phase, finish up to here, and the second phase will be conducted in the later stage. Now, this is the numerical domain, basically. It's an inverted of the nozzle domain. So consists of 15 swirl veins with the exit area to throat ratio of 5.32, with the converging angle of 30 degree and the diverging angle of 15 degree. The chord angle of the swirl vein relative to the nozzle axis is 13.6 degree. And the meshing of the model is performed using the snappy hex mesh to produce a semi-structured grid. So basically, away from the veins, the structure is the grid is structured, while close to the veins, the grid is unstructured to capture the surface of the veins. And overall, the number of hexahedral elements is 1.9 million, and the post-process was done using the ParaView and Octave. The time averaging is using trapezoidal rule. Now, this is very important. We have to verify the code used in our study. So for this reason, we use the CDV, the converging diverging verification data provided by the NASA. So basically, this case allows us to verify the solver through comparison with analytic solution, through mass conservation through the duct. So we can also verify the constancy of the total pressure through the duct, and also the consistency of axisymmetric and three-dimensional flow domains. So this is a very simplified case whereby the nozzle pressure ratio is 0.75, and there is a supersonic flow with a normal shock in the diffusing section, the plenum total pressure of 1 psi, the plenum total temperature of 100 Rankine, and also the exit static pressure of 0.75. Now, this plot compare the wall Mach number and wall pressure of the nozzles. The NASA results is represented by the orange line, and the present results is represented by the red line and also the blue dash lines. So now we focus on the red and orange line first. So basically, we can see that the present solution can accurately predict the wall Mach number as well as the wall pressure comparing to the NASA results. Okay, and also the present code also able to predict the location of the shock. Okay, we have a normal shock here. So the present solver can also predict well the location of the shock wave. Okay, and the blue one, the extended one, is where we extend the domain to include the volume beyond the nozzle outlet. Okay, and we found that due to the extension, okay, it's likely under predict the location of the normal shock wave. So we don't use this in our study, okay, and we just proceed with the normal condition as stated in the NASA webpage. Now coming to the results, okay, this is very surprisingly that the nozzle with the swirl vanes resulted in a much lower exit Mach number and velocity compared to the benchmark nozzle. Okay, so you see here, this is the Mach number contour for the benchmark nozzle without the swirl vanes, and this is the one with the swirl vanes. So we see that the exit Mach number is almost uniformly distributed at the nozzle exit plane, while for the nozzle with the vanes, okay, produce a circumferentially wavy pattern here. Okay, and due to the shock wave separation, okay, and the normal shock separation, okay, resulted in the lower Mach number at the exit plane. Now, regarding the temperature, it is also quite surprised that the temperature at the nozzle exit for the vane nozzle is much higher than the benchmark nozzle. Okay, so this indicate that the thermal energy has not been fully converted into kinetic energy. Okay, the reason for this might be due to the flow separation again, and we can see that there is a localized high temperature region, okay, particularly at the suction side of the vanes. Okay, and the maximum temperature achieved at the exit plane is about 2000 Kelvin as compared to around 750 Kelvin for the benchmark nozzle. And finally, regarding the shear stress, okay, this is the most important parameter in our study. Okay, we see that a significant increase in the wall shear stress with the incorporation of the vanes. Okay, so for the case of the benchmark nozzle, the torque is almost zero. Okay, due to the asymmetric geometrical condition of the benchmark nozzle. So the torque is produced through the swirling motion of the hot combustion product, and it imparts angular momentum to the rocket. So to conclude, the incorporation of swirl vanes in the nozzle has significantly altered the distribution of velocity, temperature, and shear stress. The swirl vanes increase the torque at the expense of performance. So it is our hope that in the future we can increase or reduce the height of the vanes gradually from upstream to downstream, okay, in order to eliminate the possibility of flow separation and also to eliminate the possibility of the induced shock waves. And we hope to investigate this further through static firing tests. I think that's all from me. Thank you.
Okay, thank you very much, Mr. Ahmad Hussein. So now I would like to open any question from audience. Yes, Mr. Hanafi, please proceed.
Sorry, Dr. Hussein, mashallah, your research is very good. Just want to know, curious to know, how do you say that having the vane will increase the stability, will improve the stability?
Okay, basically we anticipate that with the vanes, the flow will impart angular momentum to the rocket and cause the rocket to spin. So it will basically stabilize through the spinning motion of the rocket, also known as a spin stabilization.
So based on your
there are two approaches to impart stability. One is through the fin, and also the other one is through the spinning motion of the rocket.
So do you mean that if you have vanes that can produce more torque, it will be more stable?
Yes, and that has been used in many ballistic missiles.
Stable in terms of what? Is it a dynamic stability or static stability?
Gyroscopic, gyroscope.
It's
It's introducing a gyroscopic effect.
stability for during the flight.
So basically, that's the idea of rifling. Rifle bullet spin. That's why it becomes accurate. When you fire a rifle with a spin, or there are cannon now, big cannon with they call it.
So if we have many vanes with much what do you call it, narrow slots, will it increase the torque?
That what was the authors anticipated previously, Mayor. So they first anticipate that with the much number of vanes, it will increase the torque, but that's not what they observed. So the more number of vanes, the less torque produced.
Yes. So there is an optimum number actually.
They don't observe the optimum number here. Okay, but yes, that's another.
See that this sort of rocket is what you call fire and forget, because most rocket that's controlled they use gyroscope. There's a gyroscope in the in that rocket. That's the one you use to control the direction to hit the target. But some simple cheap rocket, they call it fire and forget. You spin the rocket. So this may be a good idea. You spin the rocket, it's like a rifle bullet. It's accurate to a certain point.
Yep, I agree.
Okay, thank you.
Maybe we can discuss further, Dr. Hanafi.
Of course, we understand that. That's nice, good.
Hello, Assalamualaikum.
Hello.
Hello. Assalamualaikum.
Yes. Waalaikumsalam.
Can I ask one question?
Yes.
Will the vane will the vane increase the drag of the rocket?
Will the vane increase the drag of the rocket? There is no direct. I think there is no direct relation between the vanes and the drag. Maybe there is an indirect relation. Maybe related to how the flow condition outside the rocket nozzle. But as far as the internal condition of the nozzle, I don't think there is a direct relation between the vanes and the drag, because the drag is mainly related to the wetted surface of the rocket itself, the body. I hope I answered the question.
All right, thank you.
One more thing, Dr. Hussein, why do you have the normal shock inside the divergent section?
Yes. This the verification case. We have normal shock, but this is the verification case provided by the NASA.
Verification case. Okay, I see.
The data is there on the net, so you can do verification of your code.
I see.
Okay, I think I have to stop this discussion, very interesting discussion. So thank you very much, Dr. Ahmad Hussein. So now I would like to call upon the next presenter for the paper entitled Reducing the Fuel Consumption by Using Variable Stability Technique. The authors are Yasir Abdallah Mahjub, Ola Muhammad Taha, Monzir Kamal Aldin, Ismail. So any representative from this paper to present your work? Okay, I would like to call again the paper entitled Reducing the Fuel Consumption by Using Variable Stability Technique.
Just a second, I want to share my screen.
Okay, all right.
Okay, can you see the screen?
Not yet. We are waiting. We see the white screen. Yes. Okay, now okay.
Okay.
Okay, Ms. Ola, I think you can proceed.
Okay. My name is Ola Muhammad. I have graduated recently from Sudan University. I will represent our paper, which is titled Reducing the Fuel Consumption Using Variable Stability Technique. I will begin with a problem background. Fuel has been the largest contributor to the operating cost of airline companies. Fuel prices have always been rising since 2001 to 2000. With the increasing demand for air transportation worldwide and the decreasing marginal fuel efficiency improvements, the aviation sector currently contributes to approximately 3% of the carbon emissions. This contribution will decrease to 15% by 2050. The problem statement of our research is the problem that faces aircraft manufacturers is the increasing global carbon emission caused by the increasing demand for air transportation. And for air operator is the rise of fuel prices, since fuel costs constitute the largest part of the operating cost. So the challenge is to reduce the drag of the aircraft in order to reduce the fuel consumption. The motivation of our research is, why do we need to reduce the fuel consumption of the aircraft? Firstly, it will increase the aircraft's range, decrease the operating cost, decrease the carbon emission. Secondly, how can fuel consumption be reduced? There are many ways. Some of them is reducing the weight of the aircraft using lightweight components or doing trajectory optimization. Also, reducing the drag while maintaining the same weight carrying capability. This is what we will consider in our research. Now we're going to look at some of the previous work. We have some of the ways that were used to reduce the fuel consumption. As we know, the winglets, attaching small winglets to the wingtip and orienting the winglet nearly vertical. As contribution, the lift-induced drag reduced up to 20%. Also, trajectory optimization of the aircraft, finding a periodic flight path where the fuel consumed per range is smaller for steady-state cruise. The contribution of this study is the flight endurance is improved and the fuel consumed per range is reduced. Lastly, we have optimizing the CG by building a computational model using a multi-quadrant radial basis function. It is possible to save up to 3 kilograms per minute by adopting 20% mean aerodynamic chord location compared to 27 mean aerodynamic location. So now we're gonna look at our methodology. What did we do in our research? The first step was the problem analysis stage. The central research question during this stage is to find what method is suitable in optimizing the center of gravity of the aircraft. And second, which aircraft is suitable for the study. The second stage was data collection. We chose Boeing 747-400. And the reason for that is the fuel consumption is more obvious in wide range aircraft and in long haul flight. So this is why we chose 747-400. We collected algeometric, mass, inertia, and aerodynamic properties for this aircraft. The third step was the trim calculation stage. We designed a MATLAB code that will calculate, do the trim calculation. As we see, we have here 6 equations. We solve them numerically using the MATLAB. The first equation is the normal force. The second is the axial force. The drag equation, the lift coefficient for the wing, the pitching moment around the center of gravity, and lastly, the lift coefficient for the tail. We solve this numerically to find the values for the angle of attack, the thrust coefficient, the drag coefficient, the lift coefficient for the tail, and for the wing and the total lift. So after we did this calculation, we did further calculation for a trim variable calculation. We found the value for, as you see, these are the equations. The value for the incidence angle, the elevated angle, the pitch attitude, the angle of attack for the tail and the lift to drag ratio, and some of the performance calculations, like the minimum drag speed with equivalent minimum drag speed, the stall speed, and the equivalent stall speed. And also we found the value for a neutral point for fixed control and the static model. So we did all of these calculations for different CG location and different center of gravity location. Different CG location and different speed. As we see here, this is the flow chart that shows us how the MATLAB code works. First, the user input the altitude of the flight. Then, depending on which region, gradient or isothermal, it calculates the temperature and density. We already have the geometric data stored and the aerodynamic data stored. We created two loops, one for the center of gravity and one for velocity. So it calculates the trim calculation at different velocity and different CG, and also the performance, as it's shown here. Now the fourth step is a stability and control derivative at different center of gravity location. From the trim result, the result that we obtained from the previous stage, we represented them on graph, and from these results, we calculated the stability and control derivative at different CG locations. As we see, these are the equations. The first one here is an axial force due to axial velocity, and like so on. We have an axial force, a normal force, a pitching moment due to axial velocity, due to normal velocity, due to pitch rate, due to change in normal velocity, and due to elevation. After that, the stability and control derivatives were analyzed to determine which derivatives vary with the center of gravity. Lastly, what we did, as we noticed, the equation in the trim calculation only contains polar drag and induced drag. So in this step, we added the trim drag that is caused by the elevator deflection in the tail. So now we have the value of the total drag. And from this value, we calculated our range using Friedrich range equation at different center of gravity location. These are the results. First, we obtained a lot of graphs, but now I'm presenting the most important one. The first graph here is the lift coefficient variation with the angle of attack at different center of gravity. As we see, when the CG moves up, the lift curve shifts up and the curve becomes more steep, which tells us that a small increase in the angle of attack caused a bigger increase in the lift. The second graph here is the lift to drag ratio. As we see, it decreases as we move up. The maximum value for the lift to drag is 13.84. We observed that the maximum lift to drag ratio corresponds to lift and velocity for minimum stress required. And this value is at 15% in air dam, of course. Now here, the last graph that we have, the figure gives us a visual estimate of elevated deflection required to trim the aircraft with respect to the trim airspeed. The CG from the range of 13 near aerodynamic forward to 33 at a given trim speed, less elevated deflection is required to trim the aircraft as the CG moves afterward, which reduces the trim drag. Now, this table here shows us the dependency of trim plots on CG location. Our result, we represent them in graph, as I said. So we have graphs that depend on the CG position and graphs that are independent on the CG position. Lift coefficient variation with angle of attack depends on it. Lift to drag ratio with trim airspeed also depends on it. Elevator angle deflection to trim variation with trim airspeed, and pitch angle variation with trim airspeed. The curves that are independent to the CG position are the drag variation with the trim speed, the drag polar variation with the CG, thrust coefficient variation with the trim airspeed. Now here, those are the stability derivatives, variation with the center of gravity. We have CL alpha, CZ2, CM alpha, or CM2. As we notice, we obtain the equation that will allow us to calculate a stability derivative at different CG locations. And we notice that some of them depend linearly on the CG and some of them depend quadratically on the CG. The CL alpha and the CZQ and the CM alpha, those depend linearly. But the CM2 depends quadratically on the CG. So now in this page here, this is after after we added the value of the trim drag. As we see, the red line here represents the limitation of the CG for the aircraft. This is specified by the manufacturer. So as we move up, the drag decreases. Right? The second graph here represents a lift to drag ratio. Also, as we see, the lift to drag ratio increases as we move up. And also the range of the aircraft, because the range is depends on the lift to drag ratio value. So in conclusion, this paper has focused on the problem of drag for Boeing 747, which has a direct effect on the range and therefore the fuel consumption of the aircraft. This paper firstly evaluated the trim condition at different center of gravity. The optimum location for center of gravity was obtained was 30% mean aerodynamic force based on the minimum value of total drag for a specific cruise condition. Without taking the trim drag into consideration, we did the highest value for lift to drag ratio is 13.84 at the most forward location, which is 15%. After taking trim drag into consideration, the highest value for lift to drag ratio is the most forward location, which is 30% mean aerodynamic force, which corresponds to the maximum range. The second value, we have the trim drag into consideration. That's why there is a difference. The first value we don't. The aspect control and stability derivatives were at different center of gravity. Lastly, we have the change of the gravity rotation during flight. Active gravity control gravity at optimum location. Question?
Okay, thank you very much, Ms. Ola Muhammad, for your presentation. So now I would like to open any questions from the audience. Any questions? So it seems like they have no questions. Thank you very much, Ms. Ola Muhammad, for your presentation and your time. Okay, so next will be my own paper with PMI. So let me share the slide. Okay, Assalamualaikum and very good afternoon. So today I would like to present one of our research in Aerolab, okay, which is a preliminary structural design of collar spoiler by topological optimization, which is been done a few years back. Okay, so today I just would like to share. So a spoiler is a part of aircraft being used to reduce the lift and to slow down the aircraft during touchdown. And most of spoilers are made of honeycomb sandwich core covered by the carbon fiber skins. Nevertheless, we know that the honeycomb structure are sensitive to water inclusion that could lead to the damage, for example, the skin debonding and so on, that can cause the malfunction of the spoiler. Therefore, the new spoiler with quality design has been proposed. For that reason, many studies have been conducted in the previous, for the last 2 decades, to propose a colorless design. So by replacing, the idea is to replace the honeycomb core with the composite stiffness, as shown on the picture by Lenses et al. In 1999. And since then, many attempts have been conducted to improve the spoiler colorless design, for example, by Puri et al. In last year. So by actually the idea is coming from the Lenses et al. They just want to add more ribs to strengthen the spoiler. However, to our point of view, this type of design seems complex for the manufacturing process. Therefore, we would like to propose a preliminary design concept of simple color spoiler by replacing the honeycomb core with multi-spar and multi-rib configurations using the topological optimizations. So for this study, the A320 spoiler was used as a reference, and the design requirement is based on the FAR regulations under section FAR 25.303. The strength analysis, the buckling analysis, and so on were performed using numerical modeling, Abacus software, and we use a Sci-Hill failure criterion to analyze the strength of the structure. So for the final element modeling, okay, so A320 spoiler model was developed via Abacus software, and the design specification of the original spoiler was studied for the baseline construction. So for the loading, okay, the pressure distribution used is based on when the spoiler is deployed upward to 10 degrees. And this load condition was based on the data given by the company CTRM, Composite Technology Research Measure, and calculated according to the LOMEX in 1996. And the loading, the pressure distribution as shown in this slide at the bottom left. In terms of bonding conditions, okay, at the point that we put cross here, we fix that point, and the rest connection here is allowed to rotate in Y directions. And of course, for finite element modeling, we have also performed the mesh conversion study, which is based on H refinement method in order to define the most suitable size for the meshing. So here is the results. Okay, first we simulate the baseline design, which is the core inside with the original design of the spoiler A320, and we obtain the result with a maximum Sci-Hill index is 0.6 and the maximum deflection is 12.1 millimeter. From here, we would like to remove the honeycomb and to replace this honeycomb with the composite stiffness, either as a spar or as the ribs. For the first, before we impose the rib and spar, first we simulate the spoiler without anything, without any honeycomb or any stiffness inside it. And we can see that by performing this simulation, we obtain the result, the maximum Sci-Hill index is more than 1, which is 1.9, which is show that this structure is failed. And the maximum deflection is 40 millimeter. And looking at this stress distribution and the failure on this map, contour map, it seems like the colorless spoiler must be strengthened by the multiple numbers of composite stiffness. We cannot put only one spar or only one ribs to represent the honeycomb. So for that reason, we try to do the topological optimization by using multi-spar configuration as well as multi-rib configuration, as shown here. For the multi-spar configurations, we use 13 spars, 5 spars, and 4 spar in there to replace the honeycomb. While for the multi-ribs, we use 15 ribs, 7 ribs, and 3 ribs to replace the honeycomb core. And the result I can summarize into this figure as shown. And from this figure, it can be summarized that the number of spars did not affect much the side hill failure index compared to the number of ribs as agreed by Ness et al. In 1998. We can see that when we reduce the number of ribs, then the side hill index increased significantly. Compared to the spar, when we reduce the number of spar, then the side hill index value just increased a bit. So, and then we also try to check about the buckling eigenvalue for the ribs and the spar. And this result has proven that the greatest number of ribs unable to provide competitive buckling eigenvalue as function of mass when compared to the multi-spar configurations. It can be concluded that the multi-spar configuration surpassed the multi-ribs configuration as agreed by Ness et al. In 1998. And by looking at these results, we can summarize that the model with 5 spar had more potential and it has sufficient high buckling eigenvalue and not too heavy as compared to 13 spar. Therefore, the design of the coilless spoiler with 5 spar will be used for the optimization purpose. So, a few optimizations has been done to reduce the mass of the 5 spar model without violating the buckling constraint and the side hill failure criterion. So optimization were done by reducing the plies number of spars, upper and lower skins. So we reduce, for example, for skins from 24 plies to 18 plies, and for the spar, and we reduce from 18 plies to 12 plies. And then we play around with the stacking sequence, and we can get the improved design as shown here, where the maximum side hill index is 0.79, which is safe in terms of failure mode. In terms of the failure, it is still safe. In terms of maximum deflection, it's just 7.4 millimeter, which is less than the maximum deflection obtained in the original design, which is 12.1 millimeter. And the buckling eigenvalue is 4.31, which is certified. And by doing this optimization, by reducing the number of plies and play around with the stacking sequence, we managed to reduce the weight for about 24%. Therefore, as a conclusion, multi-spar configuration were more effective in supporting the coilless spoiler than the multi-ribs configuration, as it provides slight effect on the side hill index, unlike the rib configuration. Besides that, it provides stiffness to the structure and achieve high critical buckling load. And then for a 5-spar configuration had the most potential to be further optimized for the mass reduction. The mass was reduced about 24% from the baseline and fulfill all limitation and design criteria in FAR 23.303. This is just a preliminary design, and more improvement should be done. For example, to have like a combination between the spar and the rib and so on. But we try to at this point, okay, at this moment, actually we try to design with a simplest so that it won't cause complication for the manufacturing process later on. So for that, so thank you very much. So now I would like to open if anyone have question.
Mr. Haris, may I ask a question?
Yes, please.
Okay, thank you. Really interesting research, sir. I have some question about your research, actually. First, may I know how did you calculate the magnitude of load that apply to the spoiler? And the second, is there any several terms according to FAR, or maybe any regulation about the magnitude and distribution of the load? Thank you.
Okay, because as we use 8020 aircraft as a reference, so we have to follow the FAR 23. If we use another type of aircraft, then we have to refer to another regulations, something like that. In terms of the pressure load, actually it was calculated based on the study done by Lomax, if I'm not mistaken, in 1996. And then the data for the loads is given by the manufacturer, which is one company that produce composite parts for Airbus.
Thank you.
All right, you're welcome. Any other questions?
Dr. Haris.
Yes.
Dr. Syukur ni.
Yes, Dr. Syukur.
Okay, about the deflection, what is the allowable or design spec for the deflection? Because the value that you got quite high. Is it safe or not?
Okay. I think that one from the regulation, they mention there's no mention about the maximum deflection and so on. So indeed in our case, we just focus on the more on the side hill, but the final design that we obtained, we produce less deflection compared to the original design. The original design from the Airbus is around 12.1. This is based on the numerical simulation lah. Okay, based on the numerical simulation, it's 12.1. But the one that we obtained is just 7.4. We managed to reduce the maximum deflections.
Okay. Thank you.
Okay, you're welcome. All right, any other questions before we proceed to the last presenter for the session? Okay, no. So thank you very much. Thank you very much for myself. Sorry. So now I would like to call the next presenter for the last presenter from this session with the paper entitled Preliminary Analysis of a Shooter Stabilization System for Multi-Rotor Drone Weapon System by Muhammad Husaini Zulkifli and Professor Abdul Rahim Abdul Talib.
Bismillah, Assalamualaikum. So thank you for
Waalaikumsalam.
me. Okay, I would like to share the screen.
Yes, please.
Okay, can you see?
Yes, we can see it. So please open to presentation mode. Okay, all right.
I will open presentation mode. Okay, this topic is the preliminary analysis of shooter stabilization system for multi-rotor drone weapon system. My name is Muhammad Husaini and I'll be the presenter for today, and the author is myself, including Prof. Abdul Rahim. So, we will cover the project overview, the problem statement, the project objective, literature review, methodology, result and discussion, and lastly, conclusion. So, as for the project overview, this is a collaboration with the Dream Age company, which we will develop a new study regarding a stabilization system, which will be in the middle of the drone and the payload itself. So for the payload, we will use the rifle. So as we know, it causes the problem statement of the recoil, which will give impact towards the drone of the flight stability. So with that, it will affect also the accuracy and the maneuverability afterwards. So in this objective, we would like to produce the design of the structure using the CATIA software, and then we would like to do the dynamic analysis of the recoil by using MATLAB, Simulink, and we would like to analyze the stress of the cradle designed through the finite element. But before that, there was scope and limitation. Since this is a preliminary study, there are a lot of things that we will study. We will add up later. So as for the mechanical design, as I mentioned before, we will use a CATIA software to develop the structure, and in this case, only the stabilization system. And for the analysis, is the dynamic response of a single degree of freedom. And for the material analysis, we use a Vemos stress and max principle for the cradle by using the Abacus software. So since this is a new development study, in this case, we've been researching only some part of it because it's actually a group project where it consists a large area of scope. And for the analysis, we must aware with the element that include such as the recoil impulse momentum, the shock absorber, the degree of freedom for the control design, the vibration isolator, and the manipulation process, and also the analysis of the project. So by aware of all these kind of things, we will conclude. We will observe from the benchmark that have been built before. For example, from Deep Robotic, Ticket, and also Assist Guard. And based on market research 2020, there's a lot of weaponized system UAV being developed. For example, like the ROT and many more company. So this is the opportunity for us to actually involve ourselves in developing by this UAV system to reduce the fatal injury towards our manpower from Malaysia itself. So this is the benchmark. The specification also, as we mentioned here, around like the specification of the heavy drone, and that is criteria that involved with the drone itself. So for example, like the camera, the weapon, the angle, the gimbal system for the maneuverability, and many others. So as for the methodology, we will proceed with the feasibility study, conceptual design, preliminary design, and also detailed design. For the design, we put up to the limit of the only criteria on those certain parts. And for the project requirement, we obtain from the company itself what criteria that they want. So we develop based on the request. And for the conceptual design, is more to packaging, and we do it by hand sketch. It's a normal routine for the industrial part. And then we will develop using CATIA software to proceed with the analysis later on. And by using CATIA also, we can observe the matching process, which is the availability that the limitation that they can be done. As for the key chart is really helpful. I mean, like, since it's a new development, so we can sort things up instead of just random around. So from this, we can actually limit ourselves which one we want to do and which one we have to cover. So in this case, we already come up with the design, the analysis for dynamic response, and also the application finite analysis. So this is the identification that we must understand. I mean, like for the drone and also for the payload. And we put aside the drone first, and we focus more on the payloads because the drone there's a any variety of drone that can be used later on, as long as the performance is up to the limit. And as for the payload, there are many criteria that we have to include. For example, like the mass, the length, that will affect the CG, and also the cartridge, the rate of fire, and many more. So this is the design that have been done by using the one that have been used on the normal normal system on the land. Okay, they come up with without the mitigation and also with the mitigation. Okay, this is a design sketch for the packaging, as I mentioned earlier. So we will sort things up. We will try to invest more idea based on the sketch product. So with that, we will define it whether it is a lightweight, is able to withstand the record momentum, the process, the manufacturing, the reliability, and also the safety factor. And of course, that's the most important things. But while operation and also the design process. So after we list out all the design sketches, so we will decide we're using the decision matrix. And for the decision matrix, there are criteria as we mentioned. There are points that have been evaluated, and we will give up the point later on, so that we will conclude. We can add we can add up all the points, and we find conclude that we will proceed with the 2 degree of freedom gimbal design, and also as we mentioned, there are a little bit change. We proceed with the absorber. And this is like final sketch that have been mixed up between all the design A, B, and C. Okay, as for the preliminary design, you use the open web software to identify the absorber, and this is like example of the absorber that being used. And right is the stresses of the things that we will with, whether it will exceed the yield point, either to make sure that it will not avoid deformation. I mean, like it pass the yield strength, if it pass the yield strength. So this is the details that came out from the CATIA software that have been rendered. So this is a part of the component that have been designed. So, and the frame of the cement system was made up by using aluminium. So we use the concept of thin plate instead of solid part because it will cause a lot of mess later on. And for the fixture, we have to select either we will use the welding point, the bolt and nut, because each of the fixture will cost also on the weight. So for example, we use, as we mentioned before, we use pressure and damper, and out of all, we evaluate using the CATIA software. The weight does not exceed the 7 kilo, which been as we mentioned as a requirement. So this is the dynamic response based on the significant freedom formula. So we developed a Simulink. So by referring to the formula, we came up with the graph of the recoil without mitigation and with mitigation. As you can see here, the comparison, there are many difference we can see. Which the one that with the mitigation, it came out like much faster compared to the without mitigation compared to the 0 point, which the without mitigation is undamp and recoil system with mitigation is more damped instead. Okay, and as for the finite element, since this is preliminary study and there's a lot of limitations, so we decide to focus on certain part and we conclude out the meshing later on because we using current laptop, we cannot run the full analysis of the whole cradle. So this is a material properties that have been listed down for the material for the aluminium 1100, and we come out with the result of the von Mises and the max principle. So as the von Mises is not exceed the yield point for the bearing side, so we assume that for the cradle itself, since the material properties is not quite far, not have a much gap, so I assume that it's okay since this is preliminary design, so we can improve it more later. As for the max principle, it's more to realistic number where we'll also identify the yield strength since it is thin plate. So as for the conclusion, there's a lot of safety factor that need to consider while design and also operation later. So as for mounting also, there's a lot of things that need to consider because as for the design, weight is the most scariest part of the system. And as for the mathematical model and for the final analysis, this is the preliminary design. Then there's a lot of things that can be studied later. For example, like currently we use a single shot mode, and there's actually more than that, like a burst mode, like triple mode, and other thing depends on the military itself. And as for the result of the design, we assume that this meet up the analysis, meet up the goal since it's not exceed the deformation, and also it can be seen that it be functional well if with the mitigation. So that's all for the conclusion. And for the recommendation, as I mentioned before, there's a lot of study that can be later on can be done. For example, like the previous paper, they do this study on the machine part. So to enhance, since we have a limitation on the computer, so there's not much that we can do. So we try to do our best. And as for the dynamic response also, there can be study regarding the burst mode. I mean, like there are multiple mode compared to us is a single mode. Since okay, and that's all from us. Thank you.
Okay, thank you very much, Mr. Husaini Zulkifli. So now I would like to open any question from the audience. Yes, Mr. Hanafi, proceed.
Yes, just curious. Would you include your what do you call it? Since you are doing the finite element analysis for the structure, do you think will you include the fatigue analysis instead of stress? I think that one will be more reasonable because the machine gun, isn't it? The weapon itself is in a cyclic mode.
Yes, I understand about that, but since as I mentioned before, there are many limitations while doing the analysis. So we focus on certain things instead of focus on many things. Since this is to single mode, so we consider that it's good enough for us to proceed with the stress instead of fatigue. If we do a cyclic dynamic response, then it's possible for us to continue with the fatigue analysis. So this is a preliminary study. There's a lot of condition that can be taken on. For example, like the one that we suggested. That's it.
Would you also consider to put
Yeah, of
a
course.
rocket underneath there instead of machine gun?
Actually, for the study being used by ISIS guard, there's a lot of material. There's a lot of firearm they're being used. For example, like they have a bomb. They are. And then recent study they have the rocket. But for us, we proceed with only one ammo, one firearm. So from there, we will develop more by using product and many more things. Okay, thank you.
What sort of boundary conditions do you have for this particular situation?
Sorry?
What sort of boundary conditions?
As for boundary conditions in terms of?
Because you are doing the finite element work, is that right? You're doing finite element, yeah?
Yeah, for the abacus.
Yeah, in the finite element modeling,
Okay.
what sort of boundary conditions that you have, given that you have this thing is on a drone?
Okay. So with that, I'm not sure, but I can come to you later with the one that you're asking for. If you don't mind, can you give your email so I can proceed with the boundary condition?
I mean, you did your analysis using finite element, right?
Yeah.
Okay, in doing your finite element, what are the boundary conditions that you have?
That part I need to check back with this with the one that I've been done.
Okay.
Okay. Anyone else to want to ask questions? Okay, I think it's no more. So thank you very much, Mr. Hussein Zulkifli, for your presentation.
Okay, thank you.
Okay, so we have no more presenter after this. So this will be the last presenter from Muhammad Hussein Zulkifli. So can you please unshare your screen? All right, and then how to take photo bila ada gambar ni, Cik Noh?
Siapa ni? Yang Syahirannya ni? Can Syahiran keluar dulu? You quit the room and then you come back in. Is it possible? Is Syahiran still here?
No, I think he just left, but
hold on.
It's stuck here.
It's stuck. No, okay. Macam mana? How do we get to remove the screen? I don't think we can. Stack.
Dia layout ke apa ni admin?
Tak boleh because this one is stuck here. Hold on.
Okay.
I'll just take controls.
So
cannot do much.
Cannot do much. Okay lah. Myself, my name is Haris Ahmad bin Isra Ahmad, and on behalf of the community of ISAE 2021, and on behalf of Dr. Shabuddin bin Mat, the chairman of this ISAE 2021, we would like to thank you, all of you, for participating the first seminar, ISAE 2021, and we hope that you gain something, and we hope that we can have a collaboration in the future with all the topics that have been shared and been discussed here, and hope that if in the future, if we organize the ISAE 2022, I hope that all of you might participate again. Do not hesitate. And then, do you have any questions regarding the paper or regarding anything, do not hesitate to contact the committee. And for all presenter for today, you will receive certificates, okay, for the presenter, additional certificates for all, just for the presenter. That will be emailed to you by the committee, maybe by tomorrow. Okay, and Pak Manon, do you have any final words?
No. I'm trying to figure out how to remove this screen, but I cannot do it. I was thinking of taking everybody's picture, but it's not possible now.
Don't stop the presentation, eh?
Can you start the presentation?
Syahira already.
Host is apa? Normally host can stop the presentation.
He already pressed just now, but the screen stuck.
Who's the host in here?
I also cannot remove the screen.
I do not know why.
Otherwise, we all have to left first and join back.
Maybe nak ambil gambar channel.
I cannot.
Husaini tak ada
Maybe just you just minimize the screen and make the audience screen bigger, and then
we cannot do that.
Yes,
I cannot minimize the screen.
Minimize the screen.
There's a layout option. Yes. Now it's good.
Yeah, but we can have something like this, but only one person.
Tak apalah, channel yang besar tu.
Everybody on the screen.
We can see all.
Okay. Can.
We can see all.
Select grid. Using grid. Okay.
Just do the Nafi screenshot and share in the group.
Okay, so I hope that everyone can open the camera so that we can have
okay, I've got it already. Everybody switch on your cameras. Thank you. But the number is not.
Ramai lagi yang belum buka kamera ni. Buka semua.
Tuan Johnny tak buka kamera.
Kan?
Dia tak nak buka. Nizam, Musa, Nurul Hisam, Shawin. Not going to switch on your cameras? Well, I cannot force everybody.
Okay lah, ambil dulu lah. Mana yang ada?
Okay, I've taken 2. Alright, thank you very much.
Dah Nizam masuk dah tu. Ambil sekali lagi.
Ni Syahira masuk lah. Okay. One more time.
Mana Nizam masuk? Sama je.
Nizam dengan Syahiran dah masuk.
Okay, hold on. Try again. Smile.
Okay.
Alright.
Prof tak kira, Prof.
Dah, tak sempat ready je.
Aduh, okay, try semula. 1, 2, 3. Sekejap, apa pasal? I cannot get this copied. Gosh.
Cahaya, lengkap tangan ni.
Lengkap tangan dah.
Cepat sikit.
Okay, thanks.
Alright.
Okay, so thank you very much for all presenters for today, and thank you for all the participants for joining the ISAE 2021, and hope that to see you again in the future, okay, in other seminar or in other conference. And I think all the certificates will be emailed to you by the committee later on. So on behalf of Dr. Shabuddin, we'd like to say thank you again for joining us today. And that's all. Thank you very much, and hope to see you again. Assalamualaikum.
Salam. Thank you, Dr. Haris, Prof. Ainul.
Okay.
Prof. Nazri.
Thanks very much.
Thank you. See you all.
Nazri pun masuk.
Ayah pun masuk. Nak tanya soalan tak sempat lagi.
Lambat.
Ambil sekali lagi gambar.
Baru habis sebelah sana. Cepat-cepat masuk sini.